Well, I suppose now that the interval is equal to plus minus gamma half, and I want just to briefly illustrate a very simple property of the kernel density estimation. If I calculate the integral between minus infinitum and plus infinitum of our kernel density k omega, you may notice that we can split this expression in three parts. The first is the kernel density evaluated between minus infinitum and minus 1/2. The second part is equal to the estimation between minus 1/2 and plus 1/2. Finally, the third part is the estimation of the kernel density between 1/2 and plus infinitum. But as I said, the kernel density or the indicator function assumes only two values, and the value depends on the point where we find. And of course, as you may have observed, in two cases the indicator function is equal to 0, when it is encompassed between minus infinitum and minus 1/2, and when it is encompassed between 1/2 and plus infinitum. So since it is out of the upper and lower bounds of our interval, this is equal to 0. Otherwise, in the middle case, when the indicator function is encompassed between minus 1/2 and 1/2, it is within the interval, and so it takes a value equal to 1. Therefore, if you calculate the interval, it is equal to 1. And this is basically the property of the kernel, one of the properties of the kernel density estimation. And of course, you can also observe that when the bandwidth reduces, this weighted distance xi minus x increases, and so the kernel density estimator should decrease. And this is because as n approaches plus infinitum, the value of the smoothing parameter tends to 0, and therefore in absolute value omega I tends to infinitum for every observed data which is different with respect to our actual value. Finally, I want to provide a very simple example taken from the financial analysis, and this is represented by the kernel density estimation of market returns. The example shows the estimation of the kernel density of cocoa and platinum's returns over a given time interval, which runs from 3rd of January 1991 to the 15th of May of 2008 for cocoa, and 2nd January 1991 to 2nd May of 2008 for platinum. Well, I performed this analysis with Stata, and here you can read the command, and you can see that this is the density function that comes up. This is the results of a kernel density estimation. It is the graph. It's sort of course you can see that it is not absolutely a normal distribution, but I will return the next time over the measurement of normality in statistics of finance. It is important now to understand that this is the actual way to proceed when you estimate a given density function. But as I want to show something more, I changed I changed the parameters of the bandwidth just to give you an example how the result changes according to the smoothing parameter you choose. And here you have a collection of examples where different values were used. So we start from a given so-called Emanuele kernel density, which is the default parameter in Stata, and I changed several times the smoothing parameter. I start with 50 points and then I reduce the parameter to 30 points and then again to 20 points and then again to 10 points and finally to 5 points. As you can see, that the shape of the distribution function, of course 5 points is rather an extreme example, and of course it's not really significant, but for sake of clarification, I was just to give this extreme example to see how the shape changes according to the number of points you use, and actually that means it's also the precision of your estimate changes and varies according to your smoothing parameter. That's it. The next time I will show, if you are interested in the test of normality in statistics of finance. So I hope you enjoyed this suggestion, and see you again.